Doppler radar helps with warnings on thunderstorms in several ways. First, it increases the lead time. With our conventional system right now, without Doppler, lead time is maybe 0. The tornado is formed before the warning occurs. With Doppler, we can get an average perhaps of 20 minutes lead time for people to take shelter. Also, the warnings with Doppler are more accurate. There are many fewer false alarms, perhaps 50% fewer false alarms. That will allow the public to have more confidence in the warning, and they will be more likely to follow through and take those precautions that might save their life.
Here in Boulder, Colorado, is an experimental forecast center of the future. If tornadoes are ever to be predicted more than minutes in advance, it will be at weather stations like this one.
The thing we were worried about is getting this first cell
Using a network of closely spaced observation posts, meteorologists here monitor the subtle atmospheric changes that may be associated with severe weather. They employ all the newest sensing technologies, including Doppler radar. And powerful computers allow them to display and manipulate information as never before. This image from 1884 is the first photo ever taken of a tornado. Historically, the subject of endless myth and speculation, tornadoes were once thought to cook potatoes in the ground, even fuse coins in people's pockets. A recently published idea held that tornadoes drew spin from vehicles passing on highways. More credible theories have had to do with electricity, hail, even the Earth's rotation.
If you have a tub of water and you let it still for maybe 2 days, and very carefully remove the plug and let the water drain out, and it's been shown in the laboratory that you will get a vortex which has the same sense of rotation as the Earth. A tornado would require about 3 hours to form by this mechanism, and they seem to form much more rapidly than that.
Out of systematic observations made in the past decade, a body of new theories has emerged. The mystery of the tornado is being reduced to a few key questions.
It would be awfully nice to release a track sounding right along the dry line right now. And then the convection gets...
One of the basic questions we ask ourselves is why don't all thunderstorms rotate, and why don't all those rotations or mesocyclones produce tornadoes? We need the right ingredients in terms of moisture, buoyancy, and the wind forces together to make rotation. And then there is a very, very delicate balance to get that rotation to spin up into a tornado. We find that the environment, the near environment of the storm, makes all the difference in the world.
Scientists now understand that thunderstorms gain rotation from a special combination of winds moving through their environment. Describing how these winds are organized is one of Howard Bluestein's goals in a unique set of experiments along the dry line.
What's the temperature? Temperature looks to be about 33 and a half.
Let it go. Okay.
His team releases a weather balloon. While it radios back information to a small computer, chasers track it to determine wind profiles.
And where we're located right now.
How's the signal?
The signal looks just fine. A little windy out here.
In particular, they look for wind shear, a condition in which the winds increase with height. Surface winds are slowed because of friction with the earth. While high above, the air moves faster along a narrow, high-speed river of winds, the jet stream.
Now imagine that you have a wind which is coming from this direction down here and a wind coming from this direction up here. The wind's coming much faster up here than down here. Imagine what would happen if you put a paddle wheel in the air. It would start to rotate like this. Strong wind here, weak wind here. It would begin to rotate. Now meteorologists call this measure of rotation vorticity.
When wind shear is present, rotation pervades the atmosphere, like countless rolling tubes of air. The growing thunderstorm tilts the spinning air upright, creating two vertical vortices, one on either side of it. The storm builds into the area of the counterclockwise or cyclonically spinning vortex and starts to rotate.
What happens now is that air will rise into the cyclonic part of the couplet, and the vortex tube, if you will, becomes stretched. It stretched vertically, and it shrinks in scale horizontally, very much like a skater who's spinning around. The skater brings their arms in, and they spin up. That by itself is still not enough to produce a tornado. This can produce what's called a mesocyclone, the strong rotation within a thunderstorm.
At this stage, as the mesocyclone narrows, the cloud base lowers into a beautiful and imposing form, the wall cloud. But here the mystery deepens. Out of the rotating wall cloud, the tornado seems to form suddenly without warning. What unseen events trigger the tornado? Some of the answers are appearing in storms, not over Tornado Alley, but in a computer at the National Center for Atmospheric Research in Boulder, Colorado. Scientists here simulate mesocyclones to see how and under what conditions they may produce tornadoes.
As the radars scan the storms and the chase teams are taking observations underneath these storms, they are obtaining extremely interesting observations. On the other hand, with our numerical model, we can obtain complete data sets, and if our comparisons with those observations show that we're simulating realistic storm features, then we can use that data to further understand the important mechanisms within these storms.
After it reaches maturity, the computer storm produces features seen by chase teams, a wall cloud, and nearby a clear area where downdrafts break through the cloud base. This is the same computer storm in horizontal cross-sections of 5 miles, 2.5 miles, and 800 feet above the ground. Downdrafts occur when dry air flowing around the storm at mid-levels is cooled by falling rain. The airflow patterns here suggest that downdrafts help create a new source of rotation that ultimately leads to the tornado.
Here we see the moist inflow approaching from the east and the downdraft outflow spreading out behind the storm. Where these two airstreams collide, we see a strong convergence line which separates these two very different air masses. This produces very strong rotation about a horizontal axis, which is then tilted into the vertical and strongly intensified in this low-level updraft, which we believe is responsible for the strong rotation which ultimately produces the tornado within the storm.
The mesocyclone continues to rotate, but within it, this new rotation causes rising air to move faster around a tighter spiral. In a matter of moments, it turns into a funnel, building down from the wall cloud toward the ground. The storm is now sucking in large quantities of air through the tornado's base, causing fierce ground-level winds. In most tornadoes, the updraft is constrained to the single funnel. In a strong tornado, the airflow may become so unstable that the funnel breaks down into a series of smaller vortices. For storm chasers, the computer model has created a lot of excitement, for it gives them a new way to test out their ideas and observations.
Bill, you might try time-lapse.
For example, downdrafts were first noticed in the field, and the computer helped make sense of them.
This is a spectacular wall cloud. Look at the striations, the multiple striations in this. And if there's any large hail.
Near the end of the 1985 season, Howie sees a kind of storm that seems to produce tornadoes without a strong downdraft, indicating that there are probably other mechanisms at work.
We'll just have to do our best. It's going to move right by us.
So far, I've been very impressed at how many storms, which look nearly identical to the one we saw yesterday, actually occur in nature but aren't documented. Secondly, we would like to get soundings up near these storms so that we can simulate these types of storms using the numerical model given the environment that was measured by our balloon.